we go to number 6. Again a classic, because it's a cylinder in a cylinder. And again, that means you smell Gauss's law. Both metallic surfaces, it has length L. The radius here is A, the radius here is B. There is plus Q charge only on the outer surface of this metal, but there is no charge here. At least that was the situation when Professor Becker gave me the problem. He may change his mind between now and when you see it, but that's the case, that's the situation the way I saw it. Now clearly, as a result of this plus Q charge, there will be a minus Q charge induced on the inside of this cylinder and a plus Q induced on the outside of that cylinder, but the net charge on that cylinder is 0. And you're being asked now what the E field is everywhere in space. Well, R less than A inside this metal, E is 0. That is easy. R less than B and larger than A, which means in this opening, we've done that before. I think you should do that yourself. We get E equals Q divided by 2 pi R L epsilon 0 if R is this distance. And it is pointing outwards, so I give it a R roof. We've seen this before in our previous assignment when we called Q divided by L lambda, so you may want to revisit this. It's a very famous result for a cylinder. But now, since there is no net charge on the outside, this is also true for R larger than B. Because if you make yourself a Gaussian cylinder with a radius larger than B, then the charge inside remains plus Q, because this minus Q and plus Q here cancels each other out. There is no net charge, so you find exactly the same answer. What is now the potential difference between this point and this point, between the two cylinders? And I will just write that down, shorthand notation, as VA minus VB, which is the integral in going from R equals A to R equals B of E in the cavity dot dr. That equals Q divided by 2 pi L epsilon 0 times the integral in going from A to B, R roof dot dr divided by R. Remember, the field falls off as 1 over R, because we're dealing with cylinders. This here, this dot product, is a scalar, which is the same as dr, and this integral equals the logarithm of B divided by A. And so, since this is positive, since B is larger than A, you see that A has a larger potential than B. If you want to know what the capacitance is of the cable, well, then I have to scratch my beard a little bit. Well, I don't have one. Because whenever I have to calculate capacitors, I've always been taught to put the same positive charge on one metal surface and the same negative charge on the other. Then calculate the E fields, calculate the potential difference, and then simply say C equals Q divided by V. But they don't have the same. There's no positive charge here and the same negative charge. So let me now, for the sake of the argument, put minus Q charge on the inside of this cylinder and forget the plus Q on the outside. So this outer cylinder is now charged with a net charge minus Q. Since, because of induction, all the charge goes on the inside, the location that I had is still correct, but there's no plus Q on the outside. what now is the electric field in this cavity? It hasn't changed. It's exactly the same that it was before. It's this. So what is the potential difference over this cap? It's exactly the same that it was before. It hasn't changed. In other words, the capacitance C equals that charge Q that I have here, divided by the potential difference that I calculated, which is the VA minus VB, and that we calculated here. You can read it here. And so it's done. And notice, by the way, that it is proportional with L, as it should be, because clearly the larger, the longer the cylinder is, you expect intuitively that the larger the capacitance is. But I hope you understand the subtleness of why I somehow, to be, maybe I was too much of a purist, but to be absolutely on the safe side, why I gave the outer cylinder a minus Q charge instead of it making neutral. And that the minus Q charge all goes to the inside, well, so be it. And that it turns out now that I find the same answer for the electric field in the cavity, and therefore the same answer for the potential difference between A and B. Well, maybe I was just lucky, I don't know. But I still think I did it the safest way. Okay, now we fill the capacitor with oil, and the dielectric constant is 2.2. And we do that in the area where there was vacuum before. Now E remains 0 for R less than A. That's not going to change. The new E is going to be the old E, which we calculated, divided by K. Remember, E goes down. That is for R between B and A. But for R larger than B, now the old E does not change, because there is no dielectric outside the cylinder. So now the old E that we calculated, which falls off as 1 over R, remains. So the only E that changes, that goes down by a factor K, is in between the two shells. The induced charge, or maybe the induced charge density, what you want on the dielectric, well, I would say you do that. And you may want to go back to somewhere earlier in the assignment where I did that for you on the plane parallel plates. I don't think you are going to find this too difficult. So now we have what happens with VA minus VB when the oil is in place. Well, with the oil in place, the E field in that gap goes down by a factor K. And since the potential difference is simply E times D, and since D is not changing, the potential difference goes down by that factor K. And therefore C goes up by that factor K. Think about that. C equals Q divided by V. If V goes down by a factor of K, C goes up by a factor of K. Now comes a very cute question. Let's first assume that the cavity is open. And now I, Walter Lewin, bring in this oil. And the question now is, when I bring in this oil, will this oil be sucked into this opening, or will this oil be pushed out? That means, do I have to do work to keep it in there? Well, it's a very good question. The way I would deal with it is to calculate the total electric energy in the case that the oil is in there and that the oil is not in there. So now let's write down what U is. U equals 1/2 CV squared. Of course, you could also use 1/2 QV if you like that better, or if you want to, you can write down 1/2 Q squared divided by C. It doesn't matter which one you pick. I prefer to pick this one. Q is not changing, and since the capacitance went up when I bring in the oil by a factor kappa, it is clear that U goes down by a factor kappa. Or I call it K, whatever. So what does that mean? Again, when I bring in the oil, the potential energy goes down. It's like the pencil falling. System likes to do that. Nature wants to go from high potential energy to low potential energy. So what does that mean when I bring in the oil? That the oil is being sucked in. That's what it means.